And we will have our last talk for today before the poster session by Megan Wei. And she will ask the question whether music generation models encode music theory. Megan is from Brown University.
Oh, it's over here. So you've all probably listened to a lot of music before, and when you listen to music, like even if you don't have a music background, you might be able to develop some knowledge about some patterns that you find in music. For example, you may find some songs are faster than other songs, or if you hear a note in another note, you might be able to tell they're different pitches, or one has a higher pitch than the other. Or you may even be able to tell like the distance between the pitches, which is like an interval. And in music, like in this example, it's rich with so many music theory annotations. For example, you can find tempo, the time signature, the key of the song, individual notes, intervals, chords, and so much more. And these days, if you think about music generation models, they've been trained on vast amounts of data. But the data doesn't necessarily have all these detailed music theory annotations. They generally consist of content like genre or mood. So these models aren't trained with the objective to like generate specific music theory principles. So this brings us to wonder, do music generation models encode music theory? I'm Megan, and along with my collaborators Mike, Professor Chris Donahue, and my advisor Chen, who's in the audience right here, we explore this question together. And feel free to access our paper here too. So we present this framework. So first we create the synth theory data set, which is a synthetic data set of music theory concepts. It consists of 7 music theory concepts. And then we take these music foundation models like Music Gen and Jukebox, and we feed the synth theory samples into there and extract their internal representations. Then we train a probe model to classify particular music theory classes and assess how well these music generation models encode these representations of music theory concepts. So first I'm going to dive into the synth theory data set. So this is a synthetic data set that's like programmatically generated in both MIDI and audio of these music theory concepts. It has over 100,000 total samples, and there are 7 music theory concepts. And we break these music theory concepts down into rhythmic and tonal. So within rhythmic, we have the tempo data set, which I don't hear the sound, by the way. Yeah, I'll go back. Okay, so it consists of BPMs from 50 to 210, and also 5 percussive instruments and 5 random start offsets. We also have time signatures, we have like 8 time signatures, like 5 instruments, 10 like random offsets, and 3 reverb levels to add some more like variation and make this data set more challenging. Next, in our total category, we have these 5 concepts. First, we have notes, which contains like the 12 pitch classes, like C, C sharp, D, all the way up. 9 octaves, and it's voiced in 92 instruments. So this is what a sample would sound like. We also have intervals, so it has like the 12 interval sizes at like 12 root notes, and then 92 instruments, and then 3 playing patterns. We also have scales. There are 7 modes, 12 keys, 92 instruments, and 2 playing patterns. We also created some chords. Has like 4 chord types, like major, minor, diminished, augmented, 3 inversions, like root, first, second, and then 12 notes, 92 instruments. We also got 19 chord progressions that are in 12 keys and 92 instruments. So here's one example. All right, so that's our sim theory data set. And what we do is we feed the audio into the foundation models like Jukebox and MusicGen. So how it works is like, so Jukebox consists of like a VQ, VAE, and then there's like a decoder, transformer decoder after that. And it passes the audio through the audio codec, tokenizes that, goes into the decoder, and then we extract the internal representations from the decoder model. And then for MusicGen, it has a similar architecture. It has like the encodec convolutional autoencoder, and then also like codifies the audio into like these tokens, feeds into a transformer decoder, and then like, So what we do is we take model representations from Jukebox, the decoder, and like MusicGen, the audio codec and the decoder hidden states. And we also experiment for MusicGen different size models, like small, medium, and large. Then we benchmark these foundation models with some handcrafted features like MEL spectrograms, MFCCs, chroma. We also create this aggregate handcrafted features, which combines these three handcrafted features together. Next, we'll discuss our probing experiments. So once we've extracted all the internal representations for each of the concepts, then we train a probe classifier for each concept to predict the particular class we're looking for. So for in the case of like notes, there are 12 note classes, so we'll be just like predicting it's like a C or a C sharp, D, right? Yeah, and we have some tasks that are like, multi-class classification, and tempos is more like a regression task since it's like a numeric sort of scale. So yeah, as a result, music generation models do encode music theory concepts, as seen by the high probing scores here. And also the music generative model decoder LMs, which highlighted over here, they generally perform better than the individual handcrafted features, although the aggregate handcrafted feature actually performs decently, which suggests that we should build more challenging probing data sets. So while these models can encode music theory representations, can they generate these music theory concepts? So let's generate piano D minor chord in MusicGen. So that's not quite a D minor chord, but it did get the piano timbre correctly. I've also tried having MusicGen just generate like D minor chord, and it was just some really random noise. Meanwhile, for other concepts, they tend to do a little bit better, though like precise control can be better. So for example, let's generate EDM at 50 BPM, which is very, very slow. Oh my God. So it's actually faster than 50 BPM. It's probably 90 to 100 BPM. And this one, is actually closer to 150 BPM, but then 150 BPM is like closer to the distribution of BPMs that this genre could be. So in conclusion, I think we should build these more controllable music generative models by editing the model internal representations. So this is like learning the representations for what encodes like, tempo, and then like some representations like, correspond to faster tempos, some correspond to slower tempos, and then intervening into the model's weights to change that, and then you can change a song from something that's slow to fast, or into like some precise, like fine-grained way. So yeah, thank you all for coming. Thanks for coming to BayLearn, and thank you for inviting me to give this talk. You can access the paper through this QR code. The paper also links to the website, dataset, and code. So yeah, thanks for coming.
Thank you. I have a question,
Yeah.
for starters. A lot of the more difficult concepts to capture in music are long-term dependencies.
Yeah.
It's been a long-standing problem in machine learning in general and time series, but
true.
especially in music. Did you think about ways to address that, and like in particular the music theory concept attached to longer-term dependencies as well?
Yeah, this is also like a question that we are also thinking about too, and sometimes it depends on also like the context window like the model's taken as well. So yeah, I think this is like an active question we're working on right now. At the moment, I don't have any like implementation that like shows like longer context dependencies. But one thing with the chord progressions example, like there's like different chords. There's like 4-chord chord progressions, right? With that, like if you have the same chords but in different orders, we find that these models actually like cluster those as like similar. So if you have like these 4 chords, same 4 chords but different order, then like it'll like classify like everything in that class as similar. So there is like slight like bias towards like like just like these like long-term dependencies. But in our case, like we're just like meme pooling them. So it is like that's just kind of how the representations will like look like. Yeah.
Thank you.
Yeah.
Questions from the audience?
Just curious, and thank you for the presentation. It was really interesting. Have you found in the model any music theory concepts that have been consistently producing the correct results? For example, like something like asking it to just produce a C note. Is it able to do something like that?
Yeah, so currently we're not like focused on generating the concepts, but like in terms of like classification, for the case of notes, it actually underperforms. But then for more of like the tempo time signatures classes, it performs better. So for the case of notes, it's probably because like notes are such fine-grained level detail that they may not be able to like capture that like fully. And also when you listen to like full tracks, you won't hear isolated notes. You'll probably hear like chords or like intervals, right? So like multiple notes stack on top of each other. So in some cases, it like performs better on like these like more compositional sort of concepts.
Thank you.
Yeah.
Do you foresee? Can you hear me? Yeah. Do you foresee that soon we'll be able to cluster music songs by scales and using these kind of since it's encoding music theory, so I'll be able to sort of cluster these songs that we have on Spotify by their genres, not just genre, but by modes and the time signatures and all of that.
Yeah, in terms of like clustering based on like key they're in some ways like I think you can use this approach to like label like when you have that trained probe on like identifying like scale and key, you can apply that on other models and then just like have it like predict like what like just do key detection on that. And with that, like you can also cluster it based on these like key properties. Yeah. And they've also done like clustering via like more temporal aspects, like genre and like emotions and like just like instrument types. Yeah.
We have time for one last question before the poster session. Any more questions? No, thank you. Thank you for a great talk.
Yeah, thank you.